Okay, and our next speaker is Howard Perko, and he's going to talk about the mechanics of space-time with surface tension and preferred curvature.
Thank you, James. Today's presentation is an attempt to provide a unifying theory of physics between quantum mechanics and general relativity. Many physicists have asked this question. Petra asked it this morning, how do you relate these two divergent fields? And the theory that I've proposed many years ago and been working on has to do with geometry. So like Einstein worked the rest of his career trying to figure out how to get quantum mechanics from the geometry of space-time. The question that I asked myself many years ago was, if general relativity is correct and we want to get quantum mechanics from it, and we just want to have one theory, what we have to do is figure out how to get space-time itself to curl up at small scales. How do we get space and time to like make particles? And the process that I've proposed is through surface tension. So in this lecture, I'm going to give you a background of what surface tension is and try to prove to you that space-time does in fact have surface tension. Then we're going to use continuum mechanics to write equations that govern the movement of space-time, reconfiguration of it. And then I'm going to introduce something today that is new called preferred curvature, and then show you the resulting quantum fluctuations. And then we're going to talk about cosmological implications, and hopefully I won't run over. So I think that most of us learned about surface tension in high school chemistry, and we learned about it from a glass of water. We know that the interface between liquid and air creates this fluid-like membrane, like water bugs can walk across, and it creates all kinds of interesting microphenomena, like capillary rise up into capillary tubes. But what you may not know is that surface tension happens for any interface, like these two immiscible liquids. If you look at the interface between them, it has these weird bulbous formations because there is surface tension between these two layers. Machinists know that the surface between solid and gas has a little surface called a contractile skin that affects micromachining. Even the interface between humid air and dry air is what gives clouds their interesting bulbous shapes, is surface tension. Even a barricade between people and no people, this barrier takes on wave-like properties and starts to behave as if it has surface tension. The reason is that surface tension is not from chemistry, but rather from statistical thermodynamics. Bruce, you told me earlier today you have two sons that are 22 months apart. So I imagine when they were growing up, maybe they shared a room or something like that, or at least shared a car on a family trip. And at some point, all of their stuff was scattered all over the place, all across the room. It seeks maximum entropy, right? Like this distribution I'm showing on the screen. At one point, one brother says, I don't like this mess. I want to clean up some of this entropy. So he draws a line in between and says, this is my half of the room and that's your half of the room. We're going to have a state S1 on my side of the room and a state S2 on your side of the room. And we're going to move all the stuff over to your side of the room and keep my side clean. That makes state S1 inaccessible. It reduces the probability of S1 and increases the probability the clothes are going to be scattered all over state S2. This is a higher organization. Whenever you take a continuum and push it onto one side of a barrier or another, it creates a higher order, which is a reduction in multiplicity. The reduction in multiplicity is a decrease in entropy and it requires work. Physical chemists call the work of formation of surface the negative surface energy. So hopefully you realize here, there's nothing to do with molecules. It just means that if things are organized on a surface, it has to have energy to get there because it's a higher order. The next thing you need to understand in physical chemistry is that surface energy is mechanically equivalent to surface tension. So let's take this little wireframe diagram, for example. It's got one movable side. This could be your boy's room, Bruce. And you've got the one side of the room that has all the clothes all over. And we're going to allow that boundary to move some little distance. First of all, the energy to put all the clothes on that side of the room, we're going to give Greek letter kappa. That's the energy it took to organize the room in the first place. If we move that one movable side, allowing the one brother to have a little bit more room, some distance dx, then the energy required to do that and redistribute everything is just the area that it moved times this energy density, kappa dA. Well, we can rewrite dA as simply length times the distance it moved, right? Now, if we want to figure out the force it took to push on that boundary like push it back or pull it forward, we remember that the definition of work is force times distance. So this little force arrow that I've shown can be written like this. Dx drops out of both sides, and you end up with force per length is equal to surface energy density. Force per length is surface tension. Surface tension and surface energy are the same thing in physical chemistry of surfaces. Okay, so whenever you have higher organization, you have surface tension. You have to. So why do I think space-time has surface tension? If I gave you, a ruler and said, set up a coordinate system of this room, in your reference frame, you would plot everything in this room according to 3 coordinates of space: up, down, left, right, in, out. And there would be a distribution of things in space. There's no surfaces in space. That's not what I'm talking about. But if I give you a 4th coordinate, time. Each of you has a clock, you have a watch on. What is the position of everything in this room according to your watch? If we drew a diagram of it, it would look like this. If we drop one of the coordinates of space and we just plot things left to right, in, out, and up being time, everything is at the same time for you. Each observer has 1 clock, that's it. And I say that since everything in space-time in your reference frame is organized in time at an increment of the present, that is a higher order than complete temporal dispersion. We don't have to worry about particles from the future in our reference frame. We don't have to worry about particles from the past. Everything is in the present in a reference frame with 1 clock. In fact, space-time in a Hartl's gravity book, he calls it a 3-volume and 3 surfaces. So this is our 4-dimensional view of space-time. Things are dispersed in space, organized in time. So for any arbitrary observer, this is true, and what's true for any observer has to be true for all observers. So I attest that space-time has surface tension for all observers. So let's take a closer look at one of these plots of 2 coordinates of space and 1 coordinate of time. Each one of these dots could represent a dust grain, it could represent a planet, could represent a galaxy. This is your reference frame. I don't know what you're looking at. Could be the molecules in your arm. They're dispersed in space, condensed in time. Oh, by the way, I drew the surface as undulating because Einstein taught us that space-time, it contracts, it warps around matter. So each one of these points is some kind of matter. And so I've drawn it as undulating and irregular. If we were to make a little finite element of this, it could contain one of these particles. I don't really care. What I want to know is, what does the space-time look like? And if we draw our stress energy around it, we see that you could have some matter, dp, pushing down in the time direction. That's the time component of the stress energy tensor. But surface tension tells us that you also have stresses pulling in every spatial direction. Of course, this is just one of the 3 surfaces. That means that the stress energy tensor actually looks like this. It has a mass term and 3 negative terms for surface tension. So how do we relate mass energy and surface tension? The way we do it in physical chemistry is the first equation here is the total energy of the 3 surfaces. So you just take the surface energy kappa and integrate it around all the surfaces, okay? The second equation here is just basically mass density times volume. That gives you the work of the mass density, okay? According to conservation of work and energy, you combine these together and you get the integral of surface energy over all surfaces has to equal the integral of mass over volume. If we write the divergence theorem, which is equation 6, which says that anything integrated over surfaces has to equal to the same thing, the divergence of that same thing integrated over volume, right? If we compare these 2 equations, 5 and 6, we see 7, which is that the divergence of surface tension is equal to mass. Okay, so hopefully I've convinced you space-time has surface tension. So how do we write the equations of evolution of space-time? We got Einstein's equation, but how does it evolve? And so my background is in continuum mechanics, and a lot of people don't understand how I can apply this to space-time, but continuum mechanics is not about material. Continuum mechanics is the differential geometry of a continuum, and all that means is that it's continuously differential. So as long as you believe that space-time is continuously differential, you can apply continuum mechanics to it. The only difference is that continuum mechanics, all that math evolved over the last 100 years using a positive definite metric in continuum mechanics. Of course, in In space-time, we have a pseudo-Riemannian metric. And so all we've got to do to go from Lorentzian geometry to continuum mechanics is make coordinate substitution, where we make time imaginary and proper time imaginary. The first reviewer of my first paper identified that this is creating a Hilbert space. So I'm working in a Hilbert space where I have 3 real dimensions, space, and 1 imaginary dimension, time. And I'm applying continuum mechanics to show you how that Hilbert space would evolve. The other thing that's different is that in continuum mechanics, we have a clock. So we evolve according to our clock. But in space-time, I want the clock to be part of the 4-dimensional continuum. So what parameter do I use to evolve? Martin and you guys talk about like a 4th parameter of time on the mass shell, time on the. All I'm going to do is say that there is an increment of space-time between 2 observations. You have an observation that you make, and then some observation at some space-time increment later, separated by d tau, the proper time between the observations. Okay, and d tau is going to be, you're going to define it differently depending on the observer. One person's going to say d tau was 5 seconds and 2 feet. Another observer might say, oh no, it was 10 seconds and 1 foot, because they disagree on time and space. But you know what they do agree on? The space-time separation. And the other argument I want to make is that by basically evolving my system according to proper time, that minimizes the action. Because proper time is whatever goes the straightest distance from one event to another. That's a vector. I'm saying d tau is a vector. It's a straight line from this event to the other. That automatically minimizes the action. Okay. So the way we do this in math, this is a composition of maps. So we got the one observer, the observer. We boost up to the tangent space at a point, which I think some people call the mass shell. Other people call the rest frame at a point. And we look at the evolution of that point between the 2 observations in the tangent space. Okay, I'm going to look a little closer at what that evolution looks like. So let's zoom in on that top part. In continuum mechanics, we do a polar decomposition of this vector that goes between the 2 tangent spaces. And the reason we do this is because you can separate out, there's going to be some motion of space-time. Does everybody believe that space-time flows? Pretty much. So, you know, the Earth moves over here, the space-time has to flow into its new configuration. And so the first decomposition is actually how the space-time stretches and curls. That's called the principal stretch U, which is symmetric part of the decomposition. And then the other component is how it flows, which I'm calling the boost gradient, which is orthonormal. And so when you take these and the definition of the rate of deformation tensor D is you go basically across the principal stretch, and then you go down the boost gradient, and then you come back up the transpose of the boost gradient and back down the principal stretch. So that's what I've written out here in this equation. Well, it turns out that the middle part, since those are basically rotations by an imaginary angle or boosts, they basically equal the identity. And so you're left with that the rate of deformation tensor is the square of the principal stretch. And that's how you get stretch. It's kind of like integrating around a loop and coming back. That's what we do in continuum mechanics to get strain. And curvature, by the way. And this is rate of curvature. All right, so how do we write these equations? At this point, it becomes really simple. The motion of spacetime, which is the boost gradient, is you consider the element being rigid, and it just moves from observation 1 to observation 2. And what we want to know is how it changes in momentum. So we apply the Cauchy. Am I saying it right? Is a French, brilliant French mathematician? Is it Cauchy or Cauchy? Anyway, Cauchy. He brilliant civil engineer mathematician, right? Did these momentum balance equations, but I'm doing it in 4 dimensions. So I'm including the Cauchy dimension of time, so the element could be moving in that direction. And you just balance the stress energy and treat it like stresses on the element. So I've got an imbalance pulling, you know, the element to the right in this picture and then backwards. And what it does is it changes the 4 momentum. And the way I'm writing the 4 momentum is the surface energy kappa times the area of the little element. Okay, and then I included the other dimension times the change of 4 momentum of the flow of space-time. And you get equation 11. You can do that in all the spatial directions. Then you can also do it in the time direction, but this time you got to include the sign of these little vectors pointing up for surface tension, and you got to include the mass vector pointing down or stress. And it basically gets it to equation 12. You can put all of this stuff together into one tensor, and this is the tensor that is the boost gradient in my decomposition. The next thing you do in mechanics, you write the rate of deformation tensor. So instead of assuming the element remains rigid and it moves between the two observations, you assume that it stretches and starts to curve. So it starts out with some curvature, and then at some observation later, it's recurved, okay? And we're going to use what's called the Green-Lagrange definition of the rate of deformation, which is shown as equation 14. And you're going to like it because it looks a lot like, you know, gravitational physics. What you have is you have some space-time length ds squared multiplied by, this is the change in the metric. So it's 1 plus the rate of deformation times 2. So rate of deformation is some little increment of extra length, so that the length after observation 2, in honor of my Czech friends here, I'm calling ds check. So we got ds and ds check is in the future, okay? So this is I should have called it G dot, but basically this is the change in the metric between observation 1 and observation 2. And you can rearrange that Green-Lagrange definition to equation 15, which is essentially the square of the later distances minus the square of the earlier distances, all over 2 times the square of the earlier distances. And that's what we're going to use to write our rate of deformation tensor in 4 dimensions. The other 2 equations just show you how you can break that down and linearize it to engineering strain, which is one of the cool parts of this type of mechanics, is you can linearize it. So here's all you do. You look at one element to the other in the diagram, and you set ds in the present or in the first observation equal to dy, your coordinates that you're working in the tangent space. So that might be dyj, might be along the bottom length of the element. And then you have to calculate ds future, ds check. And that little element stretches a little bit, so you got to add a little bit dy, du, dy, and so on and so forth. And anyway, it all collapses and reduces down to equation 16, which is my jj component. And you have to do this laborious repetition 4 times 4, 16 times to come up with the rate of deformation tensor in every direction, including time. So now we've written all the continuum mechanics of a 4-dimensional Hilbert space. So if you still don't believe me that any of this has to do with general relativity, let's come back to this rate of deformation tensor and note that you can write it in index notation. It looks like this. The first part is how it stretches. The second part is how curvy it is. We know in mechanics that the first part is actually the push forward of the Lie derivative of the metric, and the second part is the Gaussian curvature. If you multiply through by the metric with 2 covariant components, you can lower an index. And essentially you get what's called the extrinsic curvature plus the Gaussian curvature times the metric. If anybody recognizes this, extrinsic curvature is the Ricci tensor in 3+1 space, and the Gaussian curvature is the Ricci scalar in 3+1 space. So I've essentially just derived Einstein's equation in 3+1 space using the rate of deformation tensor. So rate of deformation is basically the push forward of Einstein's tensor. But remember, that's only one part of the polar decomposition. You also have the other motion part that we added to it. Okay, the last thing we do in mechanics is we have to have a constitutive relation in order to maintain certain symmetries. And so you have essentially the stress energy tensor equal to some constant times the Einstein tensor. In general relativity, that constant would be Newton's constant. In mechanics, it would be Young's modulus for linear elastic materials. When we met in Mexico 4 years ago, I proposed that in order to give space-time some quantum geometry, what if the coupling constant was in fact not a scalar or a constant, but it was a orthonormal tensor, and it looked like this, what I derived. And the reason this was interesting is if you have Planck's constant on the outside, and then you have 1/4 pi times the Planck length square and the time term, you multiply those together, you get Einstein's constant. But then you have 1, 1, 1 along the diagonal, which you multiply by Planck's constant, gives you this interesting fine structure of space-time. And, you know, I threw this out there. I don't know if you've seen, but at the APS meeting this year, half the people are not working anisotropic coupling constants. I think we all thought of it at the same time. I'm not sure. But I'm going to tell you today that after thinking about it for 4 more years, this just introduces too much weirdness in space. I think we would have measured it with gravitational astronomy. So I'm going to tell you that I think this is wrong. I'm going to go back to Newton's coupling constant and say that it's a constant, 1/8 pi g. And then I'm going to introduce today what's called preferred curvature. So in physical chemistry of surfaces, especially biological systems, membranes have this thing called preferred curvature. And it governs how cells separate and all kinds of biological processes where certain membranes want to have a certain specific curvature. And I'm going to suggest that that curvature is the Planck length. So this is the radius of curvature. The minimum radius of space-time curvature is the Planck length. And there's probably some reasons that we'll figure out why. I think it has to do with minimizing energy. You can't have a mass to Planck ratio any smaller than this, is what I'm suggesting. And so if you look at the bottom equation right there, it says that mass over the surface area created by a sphere of Planck radius has to be greater than or equal to surface tension, if this is our governing preferred curvature. So in other words, space-time can only curve that sharply, cannot go any sharper. That's all I'm saying with this equation. The interesting thing about that is we go back to our constitutive relation, and then we bring in this preferred curvature. Remember, in the stress energy tensor, the three spatial terms were what? Kappa, right? So let's pull in this new ratio of point mass over 4 pi times lambda p squared. And when you reduce it down, this is what you get, and you reduce a little bit more, this is what you get. Does anybody recognize what this new constitutive relation looks like at the minimum curvature of spacetime? Well, mc squared is just a chunk of energy. And then my rate of deformation tensor, the units of it are 1 over the proper time. So it's an evolutionary parameter, evolutionary function that governs how spacetime moves at a little unit of spacetime, of space increment, right? So on the left side, you have energy times time. Has to be greater than or equal to Planck's constant over 2c.
So where did you start from?
Okay, let's go back. Okay, so if you look at the top equation, all I did is say, all right, let's replace dp, the integral of dpv, by just a mass, which is just a little discrete mass. Okay, and then over on the left side, I've got kappa, and it still has to be integrated over surfaces. And I'm saying that for a polar symmetric system, the three surfaces collapse, and they're only the surface area of a sphere of Planck length as the radius is 4 pi times Planck length squared. That's the surface area of basically a Planck bubble. Planck.
So you put it in.
Yeah, I argue that that's the minimum.
Okay.
That's the minimum curvature of space-time.
That's, I got it.
Okay. So then when you take that and you put it in for kappa into the stress energy tensor, and you just algebraically reduce it, you get this. The G's drop out. This is at the minimum curvature of the Planck radius. You get essentially the Heisenberg uncertainty principle. So as long as space-time doesn't bend any sharper than this, I mean, we basically have defined the Heisenberg uncertainty principle by our constitutive relationship between curvature and stress energy. Okay, so going back to look at all of this that I did, and I know it went pretty fast, but the cool part is that I've written continuum mechanics of a Hilbert space in the boosted tangent frame, okay? And if we look at the 0,0 term in equation 13, which was it was the boost gradient one, so it governed the motion of the element. The 0,0 term has this form. It is the Klein-Gordon equation, where the thing that is wiggling is your coordinate of time. So you're sitting here thinking you're in the present, but there's actually some particles that are slightly ahead of you and some particles that are slightly behind you. And this wiggling, which is like a capillary wave following the metric of spacetime, it is spacetime rippling, is light. Light is ripples in the metric of spacetime that follow spacetime. So I'm not introducing any kind of aether. I'm saying that spacetime is the aether that is wrinkling, that light is propagating through. Okay, and then the second equation comes from basically equation 20. Equation 13, the space terms had like the gradient of kappa set equal to the change of the form momentum. You replace the kappa with the strain following the constitutive relationship, the strain from the rate of deformation, and you end up with the next equation. That's it. It's the Schrödinger equation. What is it telling us? It tells us that in a Hilbert space with one imaginary time coordinate, 3 real coordinates, that P waves, compression waves, move through Hilbert space according to the Schrödinger equation, which is just an imaginary dispersion equation. So mass moves in Hilbert space according to the Schrödinger equation. The third one I call wild particles in my paper. I'm not really sure what to call it, but what it is if you take the rate of deformation tensor, remember it had all those extra terms in the off diagonal? And if you remember, the stress energy term on the tangent space has zeros there. So according to constituent relationship, all those off diagonal terms in the rate of deformation tensor have to be zero. This is the Navier-Stokes equation, except it's got one imaginary part, right? So it's basically how Hilbert space is swirling around in space and funneling into time, creating a vortex. And what's cool about vortices is that, first of all, a regular rotational vortex is short-lived, so it would collapse. So it's a short-lived particle. If you ever take a canoe paddle and you go like this, it makes two irrotational vortices that are connected together in a U through the water. You got to check it out. And so what this suggests is that you can have two irrotational vortices in space that are connected together in time with a micro wormhole that are stable, and they'd be spinning in opposite directions. And the other thing you can have is you can have a stable irrotational vortex with a corpuscular geometry in the middle, like a little planet that's spinning, creating this irrotational vortex as well. And the other cool thing is the solutions of the Navier-Stokes equation have half-integer indices. And then, of course, we talked about the Heisenberg uncertainty principle, and there's at least 2 or 3 more waves in these equations, but I'm not a quantum mechanics guy, so I don't recognize them. So I need help like recognizing what we've got here. But to me, it's very exciting that continuum mechanics of a Hilbert space in the boosted frame gives you this interesting quantum geometry when you have a minimum preferred curvature. So to finish, last year, what I did is I tried to apply this work to cosmology. And I said that if this is your stress energy tensor, you can do a little mathematical trick where you can always add something and subtract it from the same quantity and not change it. So let's go ahead and add surface tension and subtract it from the mass term. What that does is you can now separate this tensor, where the first tensor, you get like this extra mass that we could call like dark matter. And then you get minus a negative cosmological constant, which we could call dark energy. Okay, and so by relating dp to kappa using the previous equation that I showed, not at the minimum preferred curvature, but at any bigger curvature, just using those the energy balance equations that I showed, I went ahead and re-derived Newton's theory as a first approximation. And what you have is Newton's gravity in the first term, and then you get this weird non-dimensional term. And you can calculate the velocity, orbital velocity of suns around a galaxy equal to the sine of the inclination angle. And then you got Newton's gravity again. Plus, you know how Mannheim has terms which have to do with r and r squared. I'm just suggesting it's a scalar that has to do with mass. That's what surface tension suggests. It's a mass scalar. That's it. The more mass you have, the more surface tension. So last year I only had 2 years ago I had four galaxies to compare to. Now I have 15. So I went ahead and compared this model to 15 different galaxies. How do you compare it? Well, you need mass. How do you get mass? Well, each of these galaxies, I pulled the surface brightness curve. And the assumption that you make is that a sun has a certain mass to light ratio and that all the stars in this galaxy have the same. That's the assumption we make. And so if each of these stars are producing the same amount of light as our sun, you can calculate the mass distribution from the surface brightness distribution. And what I did not do, which is different than James and his prior work, is I didn't then fit it to an exponential function and then fit the exponential to my modified gravity. I fit my model to the raw mass data. Okay, and this is what happened. The yellow dots represent astronomical measurements using Doppler shift. The dashed line represents the Newton part of these equations. And what I think is missed when you fit it to an exponential function first is that Newton predicts a much steeper slope for many galaxies because the bulge is so bright. It's like 100 times more bright than the rest of this. So most of the gravity should be in the bulge. It goes up super steep, and then it falls off at 1 over r, which is, of course, the discrepancy that everybody talks about. Where's the part that has to do with surface tension? It's way up, like 200 above this. And I'm like, oh, crud. So the one thing that I know can be changed is the mass to light ratio. We know that the main sequence of stars has different mass to light ratios. They're by magnitudes of order, right? So what if mass to light ratio of most of the stars in the center of our galaxies, which is where most of this gravity comes from, are actually much hotter, brighter stars? So I lowered the mass to light ratio until I got the model to fit. and this is down at 0.42%, and you see how the model fits the data. Newton falls off the truck. Newton is a little dashed line on the bottom, doesn't have anything hardly to do with cosmological rotational velocities, but instead the model comes down and fits quite nicely. And what's interesting to me is that changing the mass to light ratio does not change the shape of this curve. It just lowered it down to the data. I didn't manipulate the starting slope at all. This is just how the data falls down when you use a scalar component that has no R in it. It's just has to do with the amount of mass contained. So I did this for all 15 galaxies, changing the mass to light ratio for each one, saying, you know, how does this make sense? This little dwarf galaxy had the highest mass to light ratio, and so on until I got done with all 15. And I thought, all right, now how do I tell if this is right or if this makes any sense? So for reasons that'll become apparent, I went ahead and plotted these mass to light ratios that I had just found by curve fitting. And I plotted them against the square root of total luminosity. Sorry, I like looking at galaxies. And by the way, I tried to fit these to the picture so that it would be about the right scale, you know, so you could see. It's fun, right? Yeah, this one's my favorite. Okay, so I plotted these now mass to light ratios that I had just gotten from curve fitting the surface tension theory against total solar luminosity, and I got this great inverse function with an R squared value of 0.96. Why is this exciting? Because when you take this best fit function, you plug it back into the surface tension model and you solve it for the velocity at long radiuses, you get this. Basically, the velocity at extreme distances from the center of, if surface tension is correct, and if this best fit is right, gives you the Tully-Fisher relation. So I thought that was pretty exciting. I know I might still have some unit things and maybe I could be off, so these numbers may not be perfect, but I think it adds a lot of credibility to what we're doing here in terms of surface tension. Surface tension is simply just a theory that you have negative terms in the spatial diagonal of your stress energy tensor, which balance the mass term according to statistical thermodynamics of an organized system where things are organized in time. By the way, being organized in time also enforces causality, prevents faster than light travel. You know, it solves a lot of issues in physics. Continuum mechanics equations for space-time with surface tension give us a geometric form of quantum mechanics. And then you can also rearrange these terms to look like dark matter and dark energy on a cosmological scale. Our additional dark energy terms are too small to affect gravity at solar system scales, but will completely govern galaxy rotations. It gives us very low mass to light ratios right now, but the best fit mass to light ratios happen to be proportionate to the square root of luminosity and give us the Tully-Fisher relation. So if you'd like to learn more about this, I've published 3 papers so far in these proceedings, and I submitted them to the archive at Cornell University a couple months ago, and to my regret, they said that the physics community is not interested in this work in the United States. So you can only find them on my website and in the IRD proceedings. So thank you very much for you guys being so warm and welcoming to me. I appreciate it.
On my mind from the start of your talk. Great talk, by the way. You just as in merit. It's very fascinating. So, how do you respond to this critique of your initial argument, setting up the existence of surface tension, which is in that diagram you had of the particles organized in time?
See, it's
so real particles always extend in time.
they evolve, but they are not anywhere else in time other than the time on your clock. I'm sorry.
Okay, all right. So, all right, but trajectory is a state. The trajectory would go through time. So, okay.
So the whole problem is that we general relativists have gotten so used to thinking that if you talk about things being synchronous, you don't understand general relativity. But what that is that if 2 observers think things are synchronous that are moving at different velocities, then you don't understand general relativity. But there is one clock in your reference frame. Everything is synchronized to it in your reference frame. The difference is that another observer moving at another velocity, their reference frame is tilted. Their thought of time and space is tilted, but it's still organized for them in a plane. They still have one clock.
Yes.
But I agree with you. That's the hardest thing people to realize. The time, everything's organized in time. There's a great book called Now by Mueller out of California, who's the greenhouse gas guy, wrote a great book called Now that describes like how the present is really this amazing thing that no physicists talk about. Like the present is the present. Things are in the present. I'm sorry.
Yeah, I guess I wasn't necessarily saying, oh, I think you're wrong because of that. Some of it goes to the mechanics that Larry and Bill worked on, and the work I did with Bill in regard to the synchronization problem of that if you're going to build a multiple particle mechanics and you're going to define a world time along trajectories, you have to let it become desynchronous in the mechanics to other, because of this issue. And that if you have a world time along one trajectory and along the other, but you say, I need to start with initial state. Where do you pick that initial state? In a reference frame? Well, that's fine, but then you've got three particles where, then you've got arbitrary, you may start with a state that's not synchronous in any particular reference frame. What happens at that point? How do you accommodate that? So I'm not necessarily disagreeing with your assumption. I'm just sort of saying, how do you respond to that criticism? I guess one way of saying, well, it works. I get something out of it. Which is
I struggled with that. It's a great question, Matt. And it's because we draw space-time diagrams where we're looking at things that are separated from us in time. So we're plotting their location and whatever. But honestly, in a reference frame, it's completely defined by a ruler and a clock. You don't have two hands on your watch. You cannot. There's no future particles in your present. Okay. Now this plane is moving. Okay, but it's moving with you. Other particles, it's moving at a different rate. Okay, so to them, it didn't move up the same amount of time, but it's still organized for them in time. So hopefully that helps. Go ahead.
Ashish.
First, thank you for a great talk.
Thank you.
It was absolutely wonderful. When we start studying continuum mechanics, classical books like the one of Hilbert, it starts with a set of strings which are discrete, and then it takes a limit and works into continuum mechanics. Now, many people today say that space-time must be discrete and not continuous, from black hole entropy arguments and things like that. So my first question is, are you really sure that space-time is continuous?
So a good question. So first of all, let me just say this. So I'm treating space-time as okay. I'll let you deal with it while I answer the question. So I'm treating space-time as an elastic continuum. That's the difference. The whole thing is a spring. So it is quantized by the spring constant.
There's only one spring, or is it a set of springs?
It's an elastic medium. Every single part of it is elastic to the other parts because it has to be, or it will not remain a continuum geometry. It will not remain continuously differential. If you let it separate, like not spring back, then it rips and you don't have a continuous differential system.
Yes, but maybe the continuous differential system is just an approximation.
Fair enough. I mean, I agree. There's lots of points where people think space-time is made out of chunks of something. I'm saying it's a continuum, except in time, it's a membrane.
Are you acquainted with the work of Shlomo Barak?
No, maybe. I don't recognize the pronunciation.
He did something. He looked at space-time as a collection of strings connected, and he got some amazing results, like deriving mass formulas for the elementary particle.
Yeah, I mean, this would be very similar, except my elements, my springs, are the size of a differential, infinitesimal differential element. that is spring to the next infinitesimal element by this coupling constant.
Okay, good. Can you get this is a fundamental theory of everything, right? Can
That's
you
the
get the
attempt.
masses of the elementary particles?
That's a great question. And,
Okay.
I might need some help from some people for that.
It's well known in general relativity that it's not possible to define a universal now. There's a delightful book by Visser on wormholes, where at one point he makes the statement that basically any rapidly rotating general relativistic system, such as the Bell's rotating universe, standard architecture for wormholes and so forth, tends to produce closed time-like curves. Well, if you have closed time-like curves in your universe, you don't have a signal now. So that doesn't say that you're wrong here, but it says that you and general relativity are at odds, and therefore you need to resolve that disharmony.
Okay, so one of the main things, it's a great question again, is that I'm not necessarily linking any observers together. I'm just saying for a reference frame.
Yeah, the purpose of
Things are organized in
curve is
time.
an observer linked to himself. Yeah, by definition. So the observer, no doubt with the most innocent possible intentions, decided to employ a nearby wormhole time machine and chaos result, actually quite literally.
But you're saying his geometry would naturally give rise to these.
If his geometry is consistent with general relativity, and you're certainly using general relativity to develop your geometry, then general relativity, when you look at rapidly rotating systems, tends to produce closed time-like curves. Visser said that, in fact, they were unavoidable. And I commend his book on wormholes to you, because that would disagree with your approach to general relativity and therefore expose an area appropriate for investigation.
But I think you might circumvent this in some ways, because he didn't use GR to derive it. He used GR as a scaffold.
Okay, well, that would be,
to
and
compare
then you
them.
could look for the differences, and that would be interesting.
Well, as I say, so his off diagonal terms would give rise to something that might he might circumvent. I don't know. That's
Yeah, the off
complicated.
diagonal, okay. The off diagonal terms, the angular momentum type terms which are key to developing closed time-like curves, might be where you get differences with GR, but certainly you should expose those differences to establish what you're doing.
Yeah, I have more, I'll keep it a simple question, maybe it's not. It's like Robinson walking mentioned, which they use in cosmology. This is like study was another. We modeled it as a perfect fluid in space time. So you got fluids in here. Where is the surface tension? How would it come out in the Robinson walk?
So I attempted to do that in my paper last year. I wasn't sure if it was right, but I took the surface tension, which gives you the negative cosmological constant, and then attempted to calculate, the expansion of the universe, stuff like that. I got to work on that some more, but
Can you calculate the
it says that space-time is flat.
Can you calculate the Hubble constant from your work?
That's what I'm working on.
If
It's not constant, by the way. It's an evolutionary parameter.
if it's brief, and then we can go into.
Yeah, one question. So in your Klein-Gordon equation, you use T for the variable.
Well, I didn't use it. I mean, that came from, so the flow of space-time, you did the Cauchy four momentum equations in time. And what it represented is that I said that things are organized according to your clock, but I also said they have some undulation. They're not held there. Like surface tension just kind of like pulls them back. So they might want to try to go into the future, but it gets pulled back, or it might try to dip into the past, but the particle gets pulled back. And so that up-down movement of things around your reference frame is what gives us electromagnetic or Klein-Gordon equation. And it took me a hard time to think of that too, because it would suggest that that particle is moving in time differently and not staying with me, but it keeps bouncing back by surface tension. Surface tension, what pulls it back into my reference frame and stays in my present. I hope that helps answer your question.
we can go into coffee break and continue the discussions there. So let's thank Howie again.
Yeah, thank you guys for all your questions.